Chapter 21, Molecular Orbital Theory, Section 21.4, Homonuclear diatomic molecules. The molecular orbital diagram of helium-2 shows that the bond order of this helium dimer is 0. Therefore, the helium-2 molecule is very unstable. It dissociates into helium atoms spontaneously. This is the MO diagram of helium-2. We have 2 electrons in the 1s orbital on the left, 2 electrons in the 1s orbital on the right. They form sigma G bonding orbital, sigma U star anti-bonding orbital. And then we have 2 bonding electrons, 2 anti-bonding electrons. The bond order is therefore 2 minus 2 over 2. That's just 0. And also because the energy shift of this sigma U star is greater than the energy shift of this sigma G star. So actually helium-2 dimer has a higher energy than 2 separate helium atoms. Therefore the helium dimer dissociates spontaneously into helium atoms. What if we remove an electron from the helium-2 dimer? Now we have helium-2 plus. We have 2 electrons in the bonding orbital and only 1 electron in the anti-bonding orbital. Now we have a bond order. The bond order is 1/2. It's 2 minus 1 divided by 2. Therefore, the helium-2 plus is energetically stable. It has lower energy than the sum of 1 helium atom and a helium plus. This helium-2 plus does not dissociate spontaneously. We need to break a bond between these 2 helium nuclei. Although the bond order is only 1/2, there is a bond. Now let's look at the molecular orbital diagram of lithium-2. So over here we see lithium-2. First, the 1s electrons, they form sigma G and sigma star. Over here, the bond order is exactly 0. Now, the 2s orbitals, they form 2 sigma G, 2 sigma U star. And we put these 2 electrons into this lower energy, 2 sigma G bonding orbital. And over here, this is empty. So the bond order is 1. 2 bonding electrons minus 0 anti-bonding electrons divided by 2. We don't have to worry about those core electrons or core orbitals. They always cancel. And also, the core electrons are really close to the nucleus. They are attracted to the nucleus. They do not take part in any chemical reactions. We can also write out the electron configuration for a molecule, such as lithium-2. So we have 2 electrons in the 1 sigma G orbital, so over here, 2 electrons in the 1 sigma U star orbital here, 2 electrons in the 2 sigma G orbital over here, and 0 electrons in the 2 sigma U star anti-bonding orbital. Or simply we can drop the last term because we do not have any electrons in this anti-bonding orbital. And again, the bond order of lithium-2 is 1. What if we remove an electron from lithium-2? Well, that means we remove 1 bonding electron. The bond order will decrease to 1/2. Now what if we add 1 electron to the lithium dimer? Well, we can only add the electron here in the anti-bonding orbital. The bond order is also 1/2 because now we have 2 bonding electrons and 1 anti-bonding electron. We take the difference divided by 2. The bond order for lithium-2 minus is also 1/2. For convenience, after lithium-2, so we're going to talk about beryllium-2, boron-2, carbon-2, etc. We will not draw those core electrons or core orbitals for those diatomic molecules because core electrons and core orbitals are of very little interest to chemists. They do not take part in chemical reactions. Now let's look at beryllium-2. So the electron configuration of beryllium-2 is this: 1 sigma G2, 1 sigma U star 2, 2 sigma G2, 2 sigma U star 2. Remember, for lithium, we have only 6 electrons, so we stop right here. For beryllium-2, we have 2 more electrons. Now we have these 2 electrons in this 2 sigma U star orbital. So here's the situation for beryllium-2. We have 2 electrons from the 2s orbital on the left, 2 electrons from the 2s orbital on the right. Alright, and these 2s atomic orbitals form molecular orbitals, sigma G and sigma U star. we have a total of 4 electrons to allocate. Therefore, 2 electrons in this 2 sigma g orbital, 2 electrons in this 2 sigma u star antibonding orbital. What's the bond order? 0. Because we have 2 bonding electrons minus 2 antibonding electrons. It's just 0. But now, what if we remove an electron from beryllium-2? Well, look at this picture. If we remove an electron, we have beryllium-2 plus with 2 bonding electrons and only 1 antibonding electron. The bond order becomes 1/2. What if we add an electron to the beryllium dimer? Well, that means we have to put an electron on here. So over here we have this so-called 1 pi u orbital. This is formed by the interaction between a 2p orbital on the left and a 2p orbital on the right. So now we have 3 bonding electrons and 2 anti-bonding electrons. So in beryllium-2 minus, we also have a bond order of 1/2, because again, now we have 3 bonding electrons more than the number of anti-bonding electrons too. And how do we form those orbitals, those sigma and pi orbitals between 2p orbitals? Now let's look at this diagram. Between s orbital and s orbital, it's straightforward, it's a sigma bond. Between a s orbital and a p orbital, if it's head-to-head interaction, we also form a sigma bond. Between 2 p orbitals, well, we can form sigma bonds or pi bonds. This is head-to-head interaction. It's called a sigma bond. Now we are looking at pi shoulder-to-shoulder interaction between these 2 p orbitals. It's called a pi bond. And also a p orbital and the d orbital may have shoulder-to-shoulder interaction as well. It's also a pi bond over there. So you can see these 2 lobes are in phase. These 2 lobes are also in phase. Between 2 d orbitals, if you align these 2 orbitals into planes parallel to each other, you can form a delta bond. But over here, you're seeing just a simple pi bond. There's interaction between these 2 lobes and interaction between these 2 lobes. I was talking about, having 2 d orbitals in 2 different planes that are parallel to each other, and then you can have these 4 lobes overlapping with these 4 lobes. When that's the case, you have a delta bond. All right, that's more complex than this. Usually you observe delta bond in like transition metal complexes that involve 2 transition metal centers. So for now, we don't have to worry about delta bond. We don't even have to worry about those d orbitals. We just focus on this. When 2 p orbitals interact with each other via a head-to-head interaction, it's sigma bond. Shoulder-to-shoulder interaction, that's a pi bond. So now we can form a 2 degenerate pi bonds, and over here this is a sigma bonding orbital, and then we can also form 2 pi type anti-bonding orbitals and 1 sigma u star anti-bonding orbital. Now let's look at the symmetry over here. This is 2 sigma g, 2 sigma u star. But now this pi bonding orbital has a u symmetry. And why is that? Now look at this. G and u stand for symmetric and anti-symmetric with respect to the center. So we have the center here. And how do we know it's symmetric or anti-symmetric? With respect to the center, we just need to draw an arrow that passes through the center. So I'm going to draw an arrow here from this to this. Now you look at the 2 ends of the arrow. They have different colors. That means this is anti-symmetric. Alright, draw an arrow that passes through the center of this diatomic molecule. And I'm going from gray to white. Therefore, it's anti-symmetric. We can draw an arrow this way, from gray to white, or from white to gray. The color changes. It's anti-symmetric. Therefore, this bonding orbital is pi sub u. Now let's look at this head-to-head interaction. Again, there's a center here. You draw an arrow. It's going to be from gray to gray, same color. Therefore, this is symmetric with respect to the center of this diatomic molecule. Therefore, this symmetry is G. Again, the 2p interactions result in 6 molecular orbitals because we have 6 2p orbitals from the 2 atoms. In total, 6 atomic orbitals can be used to make 6 MOs. Now, among the 6 MOs, 3 are bonding molecular orbitals, 3 are anti-bonding molecular orbitals. The head-to-head interaction results in sigma bonding orbital or sigma star anti-bonding orbital. The shoulder-to-shoulder interaction results in either pi or pi star orbitals. So now let's look at this kind of diagram. We have 2p orbitals. They can interact in two different ways. Head to head, you get sigma bonding orbital and sigma star anti-bonding orbital. Shoulder to shoulder, you get pi sub u bonding orbital and pi sub g anti-bonding orbital. So now let's look at those graphs. First, head-to-head interaction. So this head-to-head interaction, it's constructive because in the middle you have white and white overlap. It's sigma. Now over here, all right, this is still head-to-head interaction, so it's sigma bond. But look at the colors. This is white, and this is this is, let's say, blue. So when you have white and blue, this is actually sigma star. This is sigma star. There's a nodal surface in the middle. There is some error in the color over here. This part should be green color. This part should be white color. Sorry about this. I kind of got the picture from Wikipedia, but there's error with the colors in this lobe and in this lobe. This is sigma star. Now let's look at pi bond. When you look at pi bond, it's definitely shoulder-to-shoulder interaction, and it's constructive interference. Blue to blue, white to white. It's constructive. Over here, pi star. Still, it's shoulder-to-shoulder interaction. Therefore, this is pi type orbital, and this is anti-bonding because we have on top we have blue and white, on the bottom we have white and blue. Different colors because they're out of phase. When they are out of phase, well, there's gotta be a nodal surface in the middle, and this is a anti-bonding orbital due to the destructive interference between these two p orbitals. Now let's look at this boron 2. In boron 2, we have 2 more electrons in beryllium 2. So in a boron atom, we have 2 electrons in the 2s orbital and 1 electron in the 2p orbital. And now let's look at the 2s orbitals. They can form sigma g, sigma u star. You put 2 electrons here, 2 electrons here. We have 2 bonding electrons, 2 anti-bonding electrons. They cancel. So this part, although it's not core electrons, not core orbitals, but this part is also a little boring over here because, again, the number of bonding electrons cancel the number of anti-bonding electrons. We have a bond order of 0. Now let's look at the interactions between 2p and 2p. So we have 3 2p orbitals on the left, 3 2p orbitals on the right. We have a total of 6 atomic orbitals to start with. We need to make 6 MOs. Which 6 MOs? We will see some pi orbitals, some sigma orbitals. When we have shoulder-to-shoulder interaction, pi orbitals. When we have head-to-head interaction, sigma orbitals. And also we have pi-type bonding orbitals versus pi star anti-bonding orbitals. Why is that? We can have constructive interference. That means overlap. Or destructive interference. That means there's a node in the middle. Now let's look at those situations. First, shoulder-to-shoulder interaction, constructive interaction. We have 2 degenerate pi orbitals, pi sub u with u symmetry. Now we can put these 2 electrons in here because we need to put 2 electrons in 2 degenerate orbitals. We have to separate these 2 electrons because they repel each other. And because of the Hund's rule, we need to have maximize the spin. So we have spin up and spin up over here. And this is boron 2, the boron dimer molecule. This is the MO diagram for this boron dimer. What's the bond order? 2 bonding electrons down there, 0 anti-bonding electrons. Therefore, the bond between the 2 boron atoms is a single bond. This is a single bond. It's really weird. The bond order is 1. It's a single bond. But in this single bond, you actually see 2 1/2 pi bonds. So you have 1/2 pi bond over here, another 1/2 pi bond over here. So let's say, well, if we put these 2 boron atoms on the z-axis, so we have a pi bond formed between the 2px orbitals and another pi bond between the 2py orbitals. And also the bond order of the pi bond from the 2px orbitals is 1/2, and the bond order of another pi bond is also 1/2. So although we say it's a single bond, it's actually made of 2 1/2 bonds. It's kind of really strange. Now let's look at the electron configuration of boron 2. 1 sigma G2, 1 sigma U star 2. Those are core electrons, core orbitals. And now we have 2 sigma G2 over here and 2 sigma U star 2 over here. Finally, 2 electrons that can make bonds. They occupy the 2 degenerate pi U orbitals. One here and one here. And what about boron 2 plus? We have boron 2 plus. We need to remove an electron, then the bond order is just 1/2. What about boron 2 minus? That means we add an electron. So how do we add an electron? We add an electron here or here. And then we have 3 bonding electrons. The bond order is 1.5. What about boron 2 minus? When you have boron 2 minus, we put an electron here, another electron here. Now we have a bond order of 2. We have 2 whole pi bonds. Alright, so that's the situation over here. And also in the ground electronic state of boron 2, we have 2 unpaired electrons. So these 2 are unpaired. They have parallel spin. Each electron is going to generate a magnetic moment due to the electron spin, and the electron spin of these 2 electrons do not cancel, because based on Hund's rule, we need to maximize the spin. It's either alpha alpha or beta beta. Either way, you have a net electron spin. That means you have a net non-zero magnetic moment. And boron 2 may be weakly attracted to the poles of a strong magnet. And we say boron 2 is paramagnetic. It's paramagnetic. Each boron 2 molecule may be considered as a very small, very weak magnet due to its non-zero net electron spin. So again, the spin of this electron does not cancel the spin of the other electron. We have a net electron spin. We have a net magnetic moment. And finally, I want to just quickly mention the number in front. So for the core electrons, we have 1 sigma G, 1 sigma U star. I didn't draw those, but now we have 2 sigma G, 2 sigma U star, and then 3 sigma G, 3 sigma U star. So we just label those sigma G and sigma U star with those numbers. And right here, this is the first time we see pi orbitals, therefore it's 1 pi U. And over here, this is the first time we see any pi G orbital, so this is 1 pi G star. So going above, you might see 2 pi U and 2 pi G stars. Now let's look at carbon 2. Carbon 2 has 2 more electrons than boron 2. So we simply fill up these 2 degenerate pi U orbitals. And the bond order is 2 for carbon 2. Well, we have a pi bond here, another pi bond here. These 2 pi bonds are perpendicular to each other. Again, let's align this molecule in the z-axis. So we have a pi sub x orbital and a pi sub y orbital. Both are doubly occupied, so we have a total bond order of 2. What if we have C2 plus? Then we need to remove an electron. The bond order becomes 1.5. What if we have C2 minus? Then we need to add an electron now in the sigma G bonding orbital. Now we have 5 bonding electrons in C2 minus. Therefore, the bond order becomes 2.5. What if we have C2 2 minus? Well, C2 2 minus has the same number of electrons as nitrogen 2. We need to put 2 more electrons here in the 3 sigma G orbital. That means we have 6 bonding electrons, 0 anti-bonding electrons. The bond order is therefore 3. And now let's look at the ground electronic state of carbon 2. We do not have any unpaired electrons. So that means we do not have any net electron spin. We do not have any magnetic moment. The net electron spin is 0. C2 is diamagnetic. In organic chemistry, we learned the bond order of C2H6, C2H4, C2H2 is 1, 2, 3. Intuitively, we would guess that when the number of hydrogen atoms decreases, we would have higher and higher bond order. But now in quantum chemistry, we learned that the bond order of C2H0 is not 4; it's actually only 2, and then we have actually 2 bonds, 1 pi x bond, 1 pi sub y bond, so only 2 pi bonds. Well, the bond order of carbon 2 may become 4 if somehow you can promote a 2 sigma U star electron to a bonding orbital. So if somehow, let's say we have 4 electrons over here, then we can somehow there are 4 bonding electrons here already. and somehow if you can promote one of these two electrons, any one of these two anti-bonding electrons, to here, all right, it takes a lot of energy to go from here to here. But let's say you have the energy, you can promote this 2 sigma u star electron to here. Now we have 2 bonding electrons, 1 anti-bonding electron, and then 5 bonding electrons here. So in total we have 2 plus 5, that's 7. We have 7, 1, 2, 3, 4, 5, 6, 7. And then we have 7 bonding electrons and 1 anti-bonding electron, and then we have a bond order of 3. So how can we have a bond order of 4? You need to promote both electrons here to here, and then we have in total 8 bonding electrons and 0 anti-bonding electrons. Again, we need external energy to promote these 2 electrons in the 2 sigma u star anti-bonding orbital to here, 3 sigma g bonding orbital, and then we will be able to have a bond order of 4 in the carbon 2 dimer. Now let's look at the electron configuration of nitrogen 2. Nitrogen 2 has 2 more electrons than carbon 2. So we're going to put these 2 electrons in the 3 sigma g orbital. We have bond order of 3. What about nitrogen 2 plus? We have a bond order of 2.5 because we need to remove a bonding electron. What about nitrogen 2 minus, the anionic molecule? The bond order is also only 2.5 because, well, if we put 1 additional electron in this diagram, you have to put that electron in the 1 pi g star anti-bonding orbital. And then we have 6 bonding electrons and 1 anti-bonding electron. The bond order becomes 2.5. Over here we have just 2 bonding and 2 anti-bonding. The ground electronic state of nitrogen 2 contains 0 unpaired electrons. You can see all electrons are paired. Therefore, nitrogen 2, just like carbon 2, nitrogen 2 is diamagnetic. So it tends to be magnetized in the opposite direction of an external magnetic field, causing a repulsive force. So nitrogen 2 has all electrons paired, therefore it's diamagnetic. So is carbon 2. Now let's look at oxygen 2. O2 is very interesting. O2 has 2 more electrons than nitrogen 2. So we have to put the 2 electrons in the 1 pi g star anti-bonding orbitals here and here. The bond order is 2 in O2. So we draw a double bond between these 2 oxygen atoms. The reason is simple. We have 6 bonding electrons, 2 anti-bonding electrons. We take the difference, that's 4 over 2, that's 2. So the bond order is just 2. What about O2 plus? Well, when we have O2 plus, we need to remove an electron, and actually we can remove a anti-bonding electron. Now the bond order is 2.5. We can also add an electron to the MO. We need to add the electron over here, and then we have 5 bonding electrons and 3 we have 6 bonding electrons in total and 3 anti-bonding electrons. 6 minus 3 divided by 2, that's 1.5. So if we add 1 more electron to O2, we form O2 minus with a weaker bond with a bond order of only 1.5. So the oxygen 2 molecule contains 2 unpaired electrons. Based on the Hans rule, these 2 electrons have the same spin. We want to maximize the spin, therefore the net electron spin is non-zero. We have a non-zero net magnetic moment over here, and that means each O2 is a small magnet, and O2 can be attracted by a magnetic pole. So now let's look at this video. In this video, I think the instructor pour first liquid nitrogen through this 2 poles, and there's no effect, but then the instructor poured liquid oxygen. You will see liquid oxygen can be attracted by the magnetic poles. So this is the video. I'm gonna fast forward to here. So I think it's pouring. I'm gonna go back to here so that we can see more clearly. This is liquid nitrogen. Liquid nitrogen just go through. Okay, there's no attraction at all. This is liquid nitrogen. Liquid nitrogen. All electrons are paired. This is liquid oxygen. with unpaired electrons. Okay, liquid oxygen is being attracted. Between these two magnetic poles, you see liquid oxygen is being attracted. Alright, so this MO diagram can be used to explain why O2 has a small magnetic moment. Now if we just imagine F2, we just put 2 more electrons here and here. We have 2 more anti-bonding electrons in F2 than O2. That means in F2 we have just a single bond. We learned that in general chemistry, between 2 fluorine atoms, there's only a single bond. And over here, using this MO diagram, we learned that in F2 we have 6 bonding electrons here, 4 anti-bonding electrons here, and then for F2, okay, for F2, and then 6 minus 4 over 2. That's just the bond order is just 1. All right. So what if you have F2 plus? Well, when you have F2 plus, you just put 1 more electron in here. The bond order is 1.5. What if you have F2 minus? Well, F2 minus, that means you put 2 electrons here and here, and then you put another electron in this sigma U star orbital, and then the bond order is only 0.5 in F2 minus. F2 minus has a very weak bond with a bond order of only 0.5. Alright, F2 minus has the same MO diagram as neon 2 plus. So neon 2 plus actually has a non-zero bond order. Neon 2 plus has a bond order of 1/2, the same as fluorine 2 minus, because neon 2 plus and the fluorine 2 minus have the same number of valence electrons. Finally, let's talk about this sp mixing and how does that change the order of MOs. So we'll compare the MO diagram of nitrogen 2 N2 and oxygen 2 O2 side by side. So in nitrogen 2 we have a total of 6 valence electrons. In O2 we have a total of 8 valence electrons. And on top they are the same. You have 1 pi G star, 1 pi G star, and then 3 sigma U star, 3 sigma U star. But if you look at this part and this part, compare this two, you'll see some difference. In nitrogen 2, the 1 pi U orbitals have lower energy than 3 sigma G. In O2, the 3 sigma G orbital has lower energy than 1 pi U. Alright, so what's the reason? This is actually the normal MO diagram. Why? Because usually pi-pi interaction is weaker than the sigma interaction. So supposedly the interaction between 2 orbitals to form this pi bonds or anti-bonding orbital, pi anti-bonding orbital, those kind of interaction should be weaker. That means this 1 pi U and this 1 pi G star should be closer to the center or the atomic energy level. So this is the atomic energy level, and the 1 pi U and 1 pi G star should be close to the center, and 3 sigma G, 3 sigma U star should be far away from the center over here. So this is the normal picture. But over here, why is this 3 sigma G kind of closer to the center? It's even above the 1 pi U. Okay, let's talk about the sp mixing. So sp mixing occurs when you have, for example, MO orbitals with the same symmetry. So you can see this is 3 sigma G, right? You have 3 sigma G. Below 3 sigma G, there's a 2 sigma G. There is a 2 sigma G. I didn't draw it. There's a 2 sigma G molecular orbital, right? The 2 sigma G molecular orbital is formed by the interaction between the 2s atomic orbitals in the nitrogen molecule or in the oxygen molecule. So 2s orbital, they can form 2 sigma G orbital. Now this 2 sigma G molecular orbital is a bonding orbital. 3 sigma G also is a bonding orbital, alright? And 2 sigma G and 3 sigma G, they have the same symmetry. They are both G symmetry, that means symmetric with respect to the center. They also have a same symmetry. It's called a sigma symmetry. So actually sigma and pi indicates the symmetry of the MOs as well. So, but you do need to learn more about point groups, about group theory, to understand that sigma and pi are symbols to denote the symmetry of MOs as well. So anyway, if you just look at 2 sigma g, 3 sigma g, they share the same sigma, Greek letter sigma. They share the same English letter G. That means they are both symmetric with respect to the center, and they both have the same sigma symmetry around the molecular axis. That means they can interact. The interaction between 2 sigma g and 3 sigma g will bump the 3 sigma g up and will shift the 2 sigma g down. So when two orbitals with the same symmetry interact, you will bump up the higher energy orbital even higher, lower MO even lower. So you will see this 2 sigma g in this nitrogen 2 is even lower, and 3 sigma g is bumped up. And it's bumped up so significantly, this 3 sigma g lies above this 1 pi u. So this is a normal picture, but then in nitrogen 2 we have sp mixing. We bump this 3 sigma g up even higher than 1 pi u. So that's the story about this sp mixing. You need molecular orbitals with the same symmetry to interact. When they interact, the lower MO orbital will become even lower. The higher molecular orbital will become even higher. That's why the sp mixing bumps up the 3 sigma g orbital in the nitrogen 2. But why didn't this kind of sp mixing bump up this 3 sigma g in O2? Well, it's simply because in O2, yes, this 3 sigma g is also bumped up because of the interaction between 3 sigma g and 2 sigma g. But because in O2 and also in F2, the energy gap between 2 sigma g and 3 sigma g is so large, the interaction is very, very small. So although this 3 sigma g is bumped up, but only by a little bit, not enough for this 3 sigma g to overcome, to get over this 1 pi u. So in O2 and F2, although there is also sp mixing, there's also energy shift of both 2 sigma g and 3 sigma g. Although 2 sigma g is shifted down and 3 sigma g is shifted up, but that shift is not enough for this 3 sigma g to have higher energy than 1 pi u. So that's that. For nitrogen 2 and for carbon 2, boron 2, so you have this kind of MO. For O2 and F2, you have this kind of MO. All of this is due to the so-called sp mixing.